Hello, welcome you all again to this online NPTEL course named Fundamentals of Composites and Cellular Materials. I am Tapas Laha, and today I am going to discuss about fibers, their fundamentals, and then I will talk about a particular fiber, glass fiber in this class. So, if we look back in the last class, we discussed about ceramic and polymer matrix composites, their overall properties, their application. Then we talked about classification of composite materials in terms of second phase, that is the reinforcement. We discussed about the basic attributes of this different kind of reinforcement composite materials, for example, particulate reinforced composites and fiber reinforced composites, and then we talked about structural composites. So, in today's class we will go more deeper into the fibers, we will discuss about the basic concepts, their properties, and then we will start talking about the basic synthesis techniques of fibers. And finally, we will choose different commercial fibers and we will discuss about their synthesis and properties and applications. And in today's class, at the end, I will talk about glass fibers, right. So, let us talk about the basic concept of fibers. Now, in the last class, I was discussing about the characteristic of fibers, and the first one I discussed about that high aspect ratio should be there. Now, why do we need high aspect ratio? Higher aspect ratio means higher length, lower diameter, right, or L by D ratio should be high. Now, the first reason of having higher L by D ratio is that if we have high L by D ratio or high aspect ratio, then the specific surface area of fibers increases, right. If we have long fiber, small diameter, obviously the specific surface area increases, and with increasing specific surface area, load transfer from matrix to reinforcement improves. Now, why do we care about load transfer? In the mechanics part, we will discuss about this in details, but basically the strength of matrix or strength in composite material increases because the load from the matrix through the interface gets transferred in the reinforcement, high strength reinforcement. So, maximum portion of load gets basically carried by the reinforcement material, and that is why load transfer is extremely important. And if we have high L by D ratio, load transfer becomes efficient. So, that is the first reason of having high aspect ratio. Second one is having higher flexibility. Now, from the theory of beam bending, we all know that M over I. So, M is the bending moment and I is the moment of inertia is equals to E, the modulus over the R, radius of curvature. Okay. Now, from here we get 1 over M R is equals to 1 over E I, right, and this 1 over M R is basically is the flexibility, right. So, 1 over M R. So, what we understand that 1 over M R should be high. Now, if we look back at this particular term 1 over E I, now what is I? I is basically pi, if we are talking about circular cross section of the beam or the fiber here. So, I equals to pi d to the power 4 by 64, right. These are all from the beam bending theories. So, if you look here, if you look back here, so it becomes actually basically E 64 goes at the top and E multiplied by pi d to the power 4, or from here we can write 1 over m r is proportional to 1 over d to the power 4, which has been shown here. So, you can see here that the flexibility is proportional to 1 over d to the power 4, where d is the diameter, okay, and r is the radius of curvature here, and m is the bending moment. So, the flexibility is proportional to 1 over d to the power 4, or in other way, lower the diameter, there is more flexibility. A nice graph has been shown here, where actually the flexibility of different materials have been compared. So, this particular line basically represents the line of equivalent flexibility. That means, along this line all materials are having same flexibility. So, you can see here where you have higher modulus like alumina or SiC, which are having very high modulus. To have high flexibility of such materials, we have to reduce the diameter to a greater extent. On the other hand, the materials which are not having very high modulus, for example, glass, okay, in those cases we can actually, or we can talk about polymeric fibers like nylon, which are having very low modulus. In those cases actually we have the luxury of having large diameter fiber, still achieving good amount of flexibility. So, the nutshell is that if we talk about very high modulus fibers, we have to see that the fiber diameter is low enough, so that we attain a good amount of flexibility in those high modulus fiber materials. High aspect ratio, that leads to better load transfer and more flexibility. Okay. The next point, which is again very important for fibers, is that it must have very good mechanical properties in terms of high fracture and flexural strength and high stiffness. Obviously, these fibers will be used in different environments. So, the fibers must be resistant to chemical attacks, and damping property should be, in certain applications, damping properties of fibers should be very good. So, these are the ideal characteristics of fibers. Okay. Now, another very important factor here is that if we, the advantage of going for higher aspect ratio or basically lower diameter is that on all these three graphs where we are showing UTS, Young's modulus and fracture strain, we can see clearly that with increase in fiber diameter, actually these values are decreasing. Very interesting point here. The material remains same, but as we decrease the fiber diameter, the modulus and the strength increases, and that is just because as we decrease the fiber, the imperfections or the defect density in the fiber decreases in terms of grain boundaries, antiphase boundaries and all those things. Okay. Because as you decrease the particle, the fiber diameter, in one cross section you have less number of grains, that means less amount of grain boundary area, and less grain boundary area means less imperfection, less defect density, and that leads to increase in the strength and the modulus. Okay. So, yes, in all means we should look for lowering the fiber diameter and having higher length of fibers. Having said that, now let us discuss what kind of different fibers we have. So, obviously, we have different kind of natural and synthetic fibers. In the natural we have coir, we have jute, okay, rami, sisal, different cotton fibers. So, different kind of natural fibers are there. In this particular course, we will talk about synthetic fibers, for example, glass fibers or aramide fibers, polymeric fibers, steel fibers or carbon fibers, boron fibers. Okay. What actually we will discuss in the next few slides or next few minutes is that what are the different ways of synthesizing fibers. Okay. Now, I have a question to all of you, is that can you guys remember this particular picture? Let me tell you that whatever we do, we try to learn from nature and then we try to mimic nature. So, the fiber synthesis techniques also came from mimicking nature. Okay. So, this is actually what we are seeing. If you can identify, this is basically the fibers or the web coming out from the spider. Okay. So, how it is happening? Now, this particular area is called spinneret, and in the spinneret, the inside the sac, the spiders, they store their milk. Okay. And once they pressure apply a particular pressure through these holes, those fibers comes out, I mean that milk comes out at a very high velocity and it gets solidified. And this process, from where you have a spinneret through which fiber is coming out or spinning out. So, this process is called spinning. Same thing happens in this kind of silkworm, again same kind of you get this kind of this cocoon, and from there you get the silk fibers. So, ultimately based on this particular process, ultimately the fiber synthesis techniques were developed and it is called spinning process. And we have different kind of spinning techniques like wet spinning, dry spinning, melt spinning, dry jet wet spinning methods. And all the fibers, in fact most of the fibers actually get synthesized by these 4 techniques only, or this spinning process only. So, the first one is which is mentioned here is the wet spinning, and let us discuss about wet spinning then. So, in wet spinning what we have is that you take your precursor material in a solution, okay, and then in the solution the precursor in the solvent it makes a solution, and then you have a pump. This pump drives this solution where the precursor material is dissolved and then drives to a spinneret. The spinneret is here. Because of the pressure, this liquid, the solution which contains the dissolved precursor material, comes out at a very high velocity, and the whole spinneret is submerged inside another second bath which is called coagulation bath. Now, once this solution comes out at a very high velocity and comes in contact with the coagulation bath, coagulation process takes place. That means, the liquid now starts solidifying, okay, and ultimately you get the filament or the fiber. So, basically you have the precursor material in the powder form gets dissolved and then it comes at a very high velocity from the spinneret, and it goes through a second stage of kind of chemical regeneration, and then it actually coagulates to ultimately give you the solid fiber, and then ultimately the fiber which comes out can be moved towards the yarn to form yarn. Okay. So, that is the basic process of wet spinning. In the dry spinning, the method is similar. However, the coagulation bath is missing here. So, you can see here in the dry spinning, again you make a solution out of the precursor, and then through the spinneret it comes at a very high velocity, and where does it come? There is a chamber. Okay. In this chamber the temperature has been, so you have a heating jacket which basically increases the temperature of the chamber, and that leads to evaporation of the solution, I mean the solvent, and you get solid fiber. So, here you do not have any coagulation bath, that is the dry spinning process. In dry spinning, a volatile solvent is used to dissolve the raw material and form a solution. Okay. Finally, the filament yarn either is immediately wound onto bobbins or is further treated for certain desired characteristic of end use. Okay. Examples of dry spun fibers are has been mentioned here, like acetate, triacetate, some acrylic, modacrylics, spandex, etc. Okay. The next one is melt spinning. So, you can from the name only you can clearly understand that some kind of melting is involved here. So, yes, again the same process, you have a hopper where the melting takes place, and then there is an extruder which extrudes the or the pumps the material inside the spinneret. Okay. So, now in the spinneret, inside the spinneret you have the molten material which is coming out at a very high velocity, and you have an evacuation chamber where the molten material gets solidified to give you solid fibers. Okay. So, the fiber materials is heated above its melting point and the molten material is extruded through a spinneret. The liquid jet hardens into a solid filaments in air on emerging from the spinneret holes. Right. So, as we understand, yes, the precursor material should be meltable, but it should not be volatile. That is the first point. And another very important factor is that the precursor material should not decompose at the melting point or in the molten state. Okay. There are various examples of fibers being made by melt spinning like glass fiber, polyester, nylon, olefin, etc. Okay. So, we talked about 3 different spinning methods. One is, the first one was wet spinning, then we discussed about dry spinning, we have discussed about melt spinning, and now the last one we will be discussing about the dry jet wet spinning method. So, it is a combination of both wet spinning and dry spinning. How is it done? Again, you can see here that basically you have the first chamber where you make the solution is being made using a particular solvent, and inside the solvent this precursor material is added. So, a solution is made and then the solution gets ejected at a very high velocity through the spinneret. Now, once it comes out of spinneret, it does not go directly into the coagulation bath. If it goes directly into the coagulation bath, that we call wet spinning. Okay. But before it goes into the coagulation bath, there is a certain amount of air gap, around 1 centimeter to 4 centimeter air gap is there. So, it goes through this air gap, certain changes takes place when it goes through this air gap, and then so basically it looks like, if I stop it here, then it will look like it is a dry spinning, and then once it comes out, it moves through this air gap and then it moves into the coagulation bath. So, basically it is a wet spinning also. So, it is a combination of dry spinning and wet spinning, and that is why it is called dry jet wet spinning method. That is the basic idea of dry jet wet spinning method, and a very important fiber is being made by this dry jet wet spinning method is Kevlar or aramid fiber. So, we will discuss about Kevlar in details at some point of time. Okay. So, we have discussed about the 4 basic techniques of fiber processing, that is the spinning method, and the spinning methods are 4 different kinds. One is wet spinning, dry spinning, then we have melt spinning, and ultimately you have dry jet wet spinning method. Okay. So, now as we have learnt about the basic synthesis techniques of fibers, let us try to concentrate on different commercial fibers. As you can see, depending upon the requirement, what kind of strength and what kind of modulus is required, there is a gamut of different kind of fibers. So, you can see the metallic wires like steel, aluminum, to glass fibers, to Kevlar, to we have SiC fiber, we have boron fiber, carbon fiber, different kind of carbon fibers. Okay. So, basically it covers the whole region of strength and modulus. Whatever strength and modulus you need, based on that you choose your particular fiber and you make it. For example, glass fiber, boron fiber, carbon fiber, organic fibers, ceramic fibers. Okay. In today's class, whatever time is remaining on that, we will discuss about the glass fiber. Okay. So, let us now pick each fiber one by one and discuss about their synthesis, their properties, their applications, and etc. Right. So, glass fibers, talking about glass fibers. Obviously, the first thing comes in our mind is that what is glass, and we all understand glass means basically it is not crystalline, it is an amorphous structure. Okay. Now, amorphous structure could be both metallic and ceramic, metallic or non-metallic. In this particular class, when we are talking about glass fibers, we are talking about ceramic glasses. Okay. So, it is a non-crystalline structure, amorphous structure made of ceramic material. And what is the basic constituent in glass fibers? Obviously, it is silica or SiO2, and in SiO2 different kind of oxides are added finally to make these glass fibers. So, let us see what do we have here. Glass fibers is material made up of several fine fibers of glasses, and most common glass fibers are silica based, where different kind of oxides of calcium, boron, sodium, aluminum, other like potassium, in some cases yttrium, all different kind of oxides are actually added to make it ultimately a glass fiber. And glass fiber is the most versatile industrial material, because you will be seeing that it is not costly to make, and it has fairly good properties in terms of mechanical and chemical properties. And we find there are different kinds of forms or morphology of glass fibers, starting from chopped strand. So, these are short fibers, and then these rovings, which contains basically single fibers, continuous single fibers, and then if you take multiple fibers together, that is called yarn, and then if the yarns are basically arranged together, then you get the fabric. So, all different kinds of forms of glass fibers are there, which are being used in different applications. So, what are the applications? Yes, you can see this fuselage material are reinforced with glass. These are made of basically polymers. So, the most common use of glass fiber is to make GRP. What is GRP? GRP is glass reinforced polymers or glass reinforced plastics. So, all these applications what you are seeing, this engine case here, this storage pipe, this transportation pipe, you can see here ultimately this frames or this here the different kind of components. Again you can see here this long structures of the windmill, different components. Ultimately most of them are being made by plastics, and these plastics to improve strength are reinforced with glass, and they are called GRPs or glass reinforced plastics. Okay. Now, how is the chemical structure of glass? So, when you have SiO2, it is a particular crystalline structure. The moment you add the different oxides, it breaks its crystalline structure, it makes and then it makes it amorphous. Okay. So, that is why it is a glassy structure. From crystalline structure, after addition of the different oxides, it makes it glassy or amorphous. Basically, the SiO2 network is being broken by the other elements which you add. For example, in this case it has shown this red the elements are basically sodium. So, sodium oxide is added, and the sodium oxide breaks the crystalline nice structure of SiO2 into non-crystalline or amorphous structure. And based on these additions of oxides, what oxides are being added, at what content these oxides are added, there are different kinds of glasses. Okay. E class, C class, D class, S class, different kind of glasses are there based on these additions of the different oxides at different proportions. Okay. Some general purpose fibers are there that contain certain amount of oxides in different and certain content, and then if you want special purpose fibers, then again you change the composition of the oxides and you get. Now, the question here is that why these various oxides are added? Is it to make it glass? In the last slide you have seen that how the oxides, when the oxides, the other oxides are added, how they are breaking the crystalline structure. That means, as you add the oxide, it becomes glass. And based on the addition of the different oxides, you can see here that we get different kind of glasses, starting from E glass to C glass to D glass to S glass. So, what you are seeing here is that the different oxides are being added at different proportions, and that leads to formation of different kind of glasses, right. Now, the question here is that why these different oxides are being added? Are these being added just to make it glass? As you have seen in the last slide, that as you add the different oxides, the crystalline structure of silica is getting broken and ultimately it becomes amorphous. So, is it the reason that we add different oxides to make it glass? Actually, no. The various oxides are added with SiO2 to improve certain properties. For example, when you talk about E glass, these are basically electrically insulated glass. C glass means higher corrosion resistant. Similarly, D glass means dielectric properties are better. S glass means high temperature strength improves. Okay. So, based on what kind of oxides we add, we basically augment a certain kind of properties. It is not to make it glass, but yes, making glass has certain advantage. What is the advantage? If you remember how glass fibers are being made, I have talked about 4 different techniques, basic techniques: wet spinning, dry spinning, melt spinning, dry jet wet spinning method. Out of that, which one is being used to make glass fiber? Yes, you are right. To make glass fiber, we use melt spinning method. That means, if the melting temperature of the material is lower, it is easier. The moment you add the different oxides, the melting point of SiO2 is generally around 1700 degrees Celsius. To be precise, I think it is 1710 degrees Celsius. The moment you add these different oxides, the moment you make it glass, the melting point easily comes down 300 to 400 degrees Celsius low. Okay. So, lower melting point. So, it makes easier to make glass fiber ultimately. Okay. So, the oxides are added for 2 different reasons. Number 1, to have certain property at a higher value, and to reduce the melting point, so that fabrication or synthesis of glass fibers by melt spinning method becomes easier, right. So, yes, how glass fibers are being made here? Okay. Basically, if you look at this particular picture, it is being made by melt spinning. How? Now, the different oxides are added here, and then by batch mixing method, and then it is being carried by a hopper to the melting furnace. In the melting furnace, all the oxides together gets mixed and molten. Once you have the molten material, it comes to this spinneret with the platinum bushing, means it has certain holes, around number of 200 holes would be there, and then it comes out through those holes from this spinneret, and once it comes out, it gets solidified obviously because of the low temperature, and then basically it gets collected and winded. Okay. So, that is how glass fiber is being made by melt spinning, and as I was mentioning earlier, that glass fiber is being made by melt spinning. So, the melting point of the material should be low, so that melt spinning method becomes or process becomes easier. All right. So, yes, if you look at the different physical and mechanical properties, you can see here that the glass fibers density is not that high, in the range of 2.5 to 2.7, in that range basically. So, we can say 2.7 gram per cc, and with that you can see the tensile strength which is being attained is in the range of 3.8, 3.1, 3 to 3.8 I can say, even in some cases you can see 4.8. Okay. So, 3 to 4 GPa. Okay. With 2.5, 2.6 gram per cc density, we are getting a fairly high strength of 3 to 4 GPa. obviously it is better than any metallic material. Okay. Modulus is not on the higher side, as you can see clearly, okay, and the elongation is fairly okay, I would say, in terms of fibers. Okay. So, if we try to summarize this table, what we are seeing is that density is low, strength is quite high. So, the specific strength of glass fibers are fairly good. Okay. It is not the best. If you talk about boron fiber, if you talk about carbon fiber, they are having even higher strength, higher modulus. But to use abundantly, to use in daily applications, okay, we need to a fiber which is of lower cost, which can be made easily. Okay. Glass fiber fits well in that particular segment because of their properties. Okay. So, if you just look back once more at the different properties, you can look actually that it obviously have high tensile strength, it has dimensional stability, that means CTE value is not that high. Okay. If it is mentioned here, coefficient of linear expansion, you can see it is not very high. So, the dimensional stability is retained. Okay. Obviously, it is high heat resistance, it does not catch fire, it does not evolve any volatile substance if it is heated, and it has very good insulation property. Along with that, in certain glasses, depending upon what kind of composition or what kind of different oxides are added, it also shows very good dielectric properties. Okay. And above all, obviously, these fibers, glass fibers are economical in terms of synthesis. Making glass fibers is quite easy and economical, and that is why the use of glass fiber is everywhere. So, with that, I would like to conclude today's class. What we have discussed today, let us just look back. We have talked about fibers, their basic characteristics, that means high L by D ratio, high mechanical strength, it should have flexibility and it should have chemical inertness. Then we talked about the basic synthesis techniques of fibers. There are 4 spinning methods: wet spinning, dry spinning, melt spinning and dry jet wet spinning method. We have discussed about these different synthesis techniques, and then we started talking about glass fibers. We discussed about what is glass fiber and why do you add these different oxides, okay, basically to improve their different properties like mechanical and physical properties, as well as to lower down the melting point. I talked about various classes like C class, D class, E class and other classes, and we have talked about the synthesis of glass fiber by melt spinning, and finally, we talked about properties and application of glass fiber as well. So, in the next class, I want to continue in this particular direction. So, as we have discussed about glass fiber today, in the next class, I will talk about boron fiber and carbon fibers, and then in the subsequent classes, I will talk about Kevlar fibers and other ceramic fibers as well. So, with that, I would like to end here today. Thank you all.